Well, welcome everyone to our Discrete Math seminar. We're very happy to have Jiayuan Wang of George Washington University who's going to talk about the Hurwitz action in complex reflection groups. Take it away, Jiayuan.
Thank you, Alejandro, again for the invitation. And this is joint work with my advisor, Joe. And so we set out to answer these questions. Given the element G of a finite complex reflection group, what can we say about the structure of the Hurwitz orbit of minimum length reflection factorization, and especially when will the action be transitive? So this is our answer, which says that given an element in G and Pn, the number of Hurwitz orbits will be this big summation over all cycle partitions such that they will have the maximum value. And for each such cycle partition, we have this product going over all the parts of the cycle partition. For each part, we compute this quantity R of B, which is the GCD of M and all those cycle weights of the cycles in that part, raise that to the power of the size of the part minus 1. And one example is this. This is the example we have seen in the pre-seminar, the diagonal element in G424. So we earlier in the pre-seminar, we showed that this element has two cycle partition that will have the maximum value. So we know all the possible orbits will correspond to these two cycle partition. In the first cycle partition, applying this counting formula we have. So for the first part, this would be GCD of 4 and 2, raise that to the power of 1 minus 1, similarly for the second part. And in the third part, we compute GCD of 4 and the weight of this cycle, which is 1, the weight of this cycle, which is 3, raise that to the power of 2 minus 1, turns out that's 1. And similarly, we can apply the same thing for this cycle partition, and that gives us 2. So this shows that there is one Hurwitz orbit correspond to this first cycle partition, and there are two Hurwitz orbits correspond to this second cycle partition.
I'm sorry, can I ask you, so why, so the first number is always M, and what are the other ones? Are there for example, why there's what's the two twos and the last one?
Right, so this is the first one is 4, and these two are the cycle weights of the cycle in that part. In this part, we have two cycles. Both of them have weight 2, so that's why there are two twos there. So that's G4222, and this one, there are two cycles. The weight of the first one is 1, so that's we have 1 here. The weight of the second one has weight 3, so that's why we have 3 here. And some observation we can make with this counting formula is the following corollary. So we know that for the action is transitive, that means we want to have 1 on the left side. And then on the right side in this summation, we better just have one term in that summation. That means G should have a unique cycle partition maximizing the value. And in this product, in order for that to be 1, either all the powers are 0, so that corresponds to the size of B equals to 1, or the base is 1. So that corresponds to R of B equals to 1. So this is our description of our Hurwitz transitive elements in G and Pn. And in some cases, we can give a simpler description. When G in MPN is just a single cycle, then that means G has a unique cycle partition maximizing value because there is only one possible cycle partition. And of course, the size of that power will be 0. So a single cycle is transitive. The Hurwitz action is transitive. And then for G in G and 1n, the action is transitive if and only if G does not have two non-zero weight cycles whose weight sum to 0 mod n. So why do we have this condition? Because if there are two non-zero weight cycles whose weights sum to 0 mod m, then in order to have a cycle partition that maximizes the value, we can either put the cycles in the same part or put them into different parts. So if we have two such cycles, then we would violate this condition that a unique cycle partition maximizing value. So that's why here, in order for the action to be transitive, we don't want this scenario. And now let's get into proof ideas. Going back to our running example, this diagonal element in G424 with 3 orbits, we know that there is 1 orbit in the first correspond to the first cycle partition, and 2 orbits correspond to the second cycle partition. And so let's see what they are. So in this one, we can focus on each part individually, and these two are singletons. So really there's no surprise there. And we can just focus on the third part. This corresponds to a diagonal element that distribute weight 1 to the first weight and distribute weight 3 to the second cycle. And we can factor this starting with this transposition. And since this diagonal element is fixed, so once we decided on the first factor, the second factor is automatically decided. So we start with that and then apply. So for that reason, we know there are 4 different factorizations that correspond to this particular diagonal element. And then we take one and we just apply Hurwitz move repeatedly and see how many orbits, how many factorizations we will get in this particular orbit. And turns out all the possible minimum length factorization, they are included in this single orbit. So this is how we know that there is one orbit correspond to that cycle partition. And now let me write down a representative following this orbit. So the first one corresponds to this singleton. That will be 1 zeta squared, 1, 1. And then this will be 1, 1 zeta squared, 1. And then this will be 1 transposition, 1.
But I'm sorry, Jiayuan, let me ask. So what is it that tells you that you have, considered all of the factorizations? Like, do you rely on this graph-theoretic interpretation to make sure that you have covered all of them, or is that some other argument?
Yeah, this is a fantastic question, Theo, and it is coming up in the actual formal proof. So just hold that thought for a little bit. We'll come to that. And this is a representative factorization corresponding to the first orbit. And we can do the same thing for this second cycle partition. Well, this cycle partition has 2 parts. We just dealt with the second part, so we can focus on this part. In this part, we can build a diagonal element that assigns weight 2 to the first cycle and assign weight 2 to the second cycle as well. To factor this, again, we start with transposition, apply Hurwitz move, and turns out there are only 2 factorizations in this orbit. And then we pick another factorization that is not in the first orbit and then apply Hurwitz move to this factorization, and we found a second orbit. So, and okay, let me also write down 2 representative factorization correspond to these 2 different orbits. Again, so here, this will be this one, and then we have this zeta squared, 1, and these are the same. And the next one, this will be 1 zeta cubed, 1, and this is 1 zeta cubed, zeta 1, and these 2 will be the same as before. Okay, so in order to describe this behavior where sometimes we have a single orbit, sometimes we have multiple orbits, we define this quantity R, so which is the GCD. So in this part, this is the GCD of 4 and the 2 cycle weights. So this is 1 and 4, 1 and 3, which is 1. And then we focus on the weight of the bottom left entry of the first factor in each pair of factors. Notice that their weight, so here weight is 0, weight is 1, weight is 2, weight is 3. All of these are the same mod 1. And we do the same thing for this second part. Here GCD will be 4, 2, 2, which is 2. And then again, look at the weight of that special entry. So here we have 0, we have 2, we have 1, we have 3. And when 2 factorization are in the same orbit, their weights are the same, mod 2. So this seems to just suggest that whenever the weights are the same, mod R, they belong in the same orbit, because we can find an explicit Hurwitz move that will take us from one factorization to another. And when their weights are different, this seems to suggest that they belong into different orbits, but this is not a convincing argument because there might be some mysterious Hurwitz path that will take us from one factorization to the other when they have a different weights mod R. So in order to show they actually belong into different orbits, we think about one of the invariant of the Hurwitz action, which is in particular, so that would be the subgroup generated by the factors. So the subgroup generated by these 2 factors, they form the group G2. And for every non-zero entry in this group, we have either 1 or -1. And that is definitely not the same group generated by these two factors, because already this is a fourth root of unity. So because these two factorizations, they generate different subgroups, then they belong into different orbits. So this is how we can show in order to count the number of Hurwitz orbit, it's enough to just count how many weights, different weights we have mod R. In the first case, there is only one weight, mod R, that's one. So that's why there's only one orbit. In the second case, there are two different weights, mod R. So that's why we have two different orbits. And so this is just the general idea using this really simple example.
So you're saying here that the different weights correspond to different groups that are generated by the factorization.
Mm-hmm. Yeah, exactly. And now let me go to a more formal proof. So in the first step of this more formal proof, it involves a definition that is called a standard form factorization. So what is that? In the example we have, we focus on a part that has two zero length cycles, and their factors correspond to this graph. In general, we can have multiple number of cycles. Their graph would involve multiple pairs of parallel edges. And if the weight of this part is not zero, mod m, then we add a loop to that. But also these cycles, they can have arbitrary length. So then we just add some paths to represent the factorization. Okay, so this is a loop. Let me change to a different color to represent that. So that's a loop, okay. And this is what we call a standard form. So this is a standard form factorization. So any factorization whose graph have this particular look is called a standard form factorization. And the point of the first step is to show every minimum length reflection factorization belong to the same orbit as some standard form factorization. And this is because for some element, they may have factorization whose graph will probably look like this. Just completely crazy looking. So then the point of this step is to show that for every minimum length reflection factorization, especially the crazy looking ones, they belong in the same orbit as some nice looking factorization that we call standard form. And this is done by the work of Krugman, Benezet, and Tiger. So then in order to count the number of orbits is enough to count how many orbits that the standard form factorization they will form. And then in the next step, we show when two standard form factorization are in the same orbit, and that happens exactly when the weights are the same, mod R. So in the example, we show that when we just have one pair of parallel edges, we can just take the weight of this bottom left entry of the first factor in each pair of factors. And then generally, when we have multiple pairs of loops, we can also do the same thing. So for example, we can take this will be 1 all the way to a k. And so now instead of drawing a graph every single time when we want to mention standard form, it's enough to just look at this vector of weights. And if we have a different vector of weights corresponds to a different standard form, and turns out they are the same, mod R, then we know these two factorization are in the same Hurwitz orbit, because we can build an explicit Hurwitz path that go from this first factorization to the second factorization. So go ahead.
No, when you have a tuple, when you say modulo R, it means like entry-wise, or sorry, I guess I'm a bit confused but with tuples having mod R. Is it A1 is congruent to A prime 1 mod R, or
Right. Yeah. So here I want this A1 to be the same as A1 prime, and then A2 will be the same as A2 prime, all the way to AK will be the same as AK prime. So then this would correspond to the first pair of factors, and then this A2 would correspond to the second pair factors. And so let me say, how do we know there is an explicit path that will go from the first factorization to the second one? Well, it involves 3 special sequences of Hurwitz move. The first sequence of move is exactly the one we have seen in this example, where we just let this pair of factors interact within itself. So that's the first kind. The second kind is we can let this pair of factors, let that interact with some other pair of factors. That's the second kind. And the third kind is let this pair of parallel loops or pair of factors, let that interact with the loop if there is a loop. So these 3 kinds of Hurwitz moves will guarantee us that we can change this vector of weights to this second kind. And this is possible because there are equivalent mod R. So essentially, this is the extended Euclidean algorithm from elementary number theory. So in the second step, we show that 2 standard form factorization are in the same orbit if they have the same weights mod R. And now what remains to show is that when they are not the same mod R, then they belong in different orbits. Or in other words, in the third step, we want to find any variant that distinguishes the orbits. And the trivial case is that if the 2 orbits have different partition, then definitely we can tell them apart. And less trivial is when they correspond to the same partition. So here, let's set up what we have. We are in GMPN, and there is a part for every part in a cycle partition. For example, there are some number of cycles being put in this part, and the weight of that part is D, and the R of that part is the GCD of M and all those cycle weights. So let me just draw this standard form factorization graph again. There may be a loop, some paths. So earlier we talked about how we can take a weight and record this pair of factors. And there is a special kind of standard form factorization where all the weights are 0. So that means for each pair of factors, the first factor is always the transposition. And the subgroup generated by this particular standard form factorization, that's the group GM over R, GCD of MD over R, and N prime, where N prime may be less than or smaller to N. So that's a subgroup. And if there is another tuple of weights, that is not the same as that 0 weight, mod R, then the group generated by this one, it will not be the same as this group, but it's an isomorphic copy of this group. So in this step, we showed that 2 standard form factorization, they belong, if their weights are not the same, mod R, then they belong in different orbits because they generate different subgroups. So let me recap here. What we have done so far is in the first step, we showed in order to count the number of orbits, it's enough to count the number of orbits formed by the standard form. In the second step, we show that 2 standard form belong in the same orbit when they have the same weight mod R. And third step showed that 2 standard form that are not in the same orbit when they have different weights. So all of this buildup is to say, to count the number of orbits is enough to count the number of different weights we have mod R. And now, so for each weight, for each entry, there are different choices, and then we raise that to the size of B minus 1. So that will be the number of orbits we have for this particular part in the cycle partition. Since each part, they are independent from each other, we apply that to all the parts in the cycle partition and summing it over all possible cycle partition that maximize the value. So this is how we arrived at the counting formula in the theorem. So in order to count the orbits, we can just count how many weights do we have, how many different weights we have mod R. And to answer Theo's earlier question, this is how we know for sure that we covered all the factorization.
So that isomorphism that you have below, is it like a group theoretic isomorphism, or is it that these groups are conjugate inside?
Conjugation. There's a conjugation map that takes every element from this copy to a different copy. So this also implies that all of these different copies, they share the same collection of diagonal elements because it's conjugated by a diagonal element.
And that diagonal element, does it belong to the group that you start with, the GMPN, or can it be in the normalizer in GM1N or something?
So yeah, it's not going to be necessarily in GMPN, but it will definitely be in GM1N.
I see. Okay.
So this wraps up our proof. And the last step also leads us to another theorem, which states that for any finite complex reflection group and the two minimum length factorization of the same group, they generate the same orbit if and only if they generate the same group and they have the same conjugacy classes of factors. So if we're only talking about G and Pn, then this condition is enough to distinguish when two factorization are in the same orbit. But this additional condition is necessary because in some elements in the exceptional ones, and in fact, Theo has found an element in G16 that has two minimum length reflections. They generate the same group, but they are not in the same orbit because they don't have the same conjugacy of classes. But with these,
sorry, if you could repeat again, when is the first condition enough? When is just the groups being the same?
Right, when we are only talking about GMPN. So when we only have GMPN, then this condition is enough to say when two factorizations are in the same orbit or not. But this condition is necessary to include all the exceptional ones. And this is the end of the proof for our counting theorem. And let me say another related topic. In the pre-seminar, I introduced you to this theorem by BGRW as one of our motivating theorem. So they give a complete classification of Hurwitz transitive element in finite real reflection where they are parabolic quasi-Coxeter. So then we go ahead and found quasi-Coxeter elements in GMPN. But first, let's define what's a quasi-Coxeter. So for an element in the group G, if every minimum length factorization generates the whole group, then we say this is a quasi-Coxeter element. And here we have an additional condition on this rank, on the reflection length, because in a complex reflection group of rank n, the Coxeter element only exists at reflection length n. So then to be consistent with that, we study quasi-Coxeter also of reflection length n in GMPN. And here is our classification of all such elements. And also, let me just say one more bit about what this definition. So in order for the factorization to generate the whole group, then we should only have one part in the cycle partition where all the cycles are in the same part. Otherwise, we wouldn't be able to generate the whole group. So then the side.
Oh, so sorry to interrupt. I'm sorry. So again, for quasi-Coxeter, so for example, in the symmetric group, every element is quasi-Coxeter, or what's an example?
N cycle. N cycle.
Only N cycles. Okay.
Yeah. Were you gonna say something, Theo?
No, I was going to say every element is parabolic quasi-Coxeter in the symmetric group. That's what
That's right. Thank you. Yeah, that's exactly right. And then, so in order to generate the whole group, we better have a one-part cycle partition. And then to make sure we have all the weights, then the R of that part should be 1. With that in mind, in group GM1N, in order to generate the underlying symmetric group, then we need a N cycle. But to make sure we have all the weights, then we need to include a loop factor that is of primitive weight mod n. So here, all the quasi-Coxeter element of length n are exactly the N cycles with weight primitive mod m. And then in MMN, again, in order to generate the underlying symmetric group, we need an n cycle. But to cover all the weights, we no longer have this loop because the weight of that loop is not a multiple of m. So we can add another edge. So this creates 2 cycles. In order to make sure all the weights are generated, then we require, and so that corresponds to this condition. That means the weights of the 2 cycle should be primitive mod m. And also this has reflection length n. And in GMPN, when p is smaller than m, bigger than 1, we don't have such quasi-Coxeter elements because this group needs at least n+1 generators. So that's what we have. This is our description for such element. And one more thing that I want to say is that this definition here, we require every minimum reflection length. So this is actually the strong quasi-Coxeter element. And if we want to talk about weak quasi-Coxeter element, that means there just exists one. As long as we can find one minimum length factorization that generates the whole thing, then this element is considered a weak quasi-Coxeter element. And in GMPN, the strong and weak quasi-Coxeter, they are the same definition. But in the exceptional case, they are not the same. So recently, Joel has found an element in G10 who has 2 minimum factorization. One generates the whole group, but the other does not. So in the exceptional case, these two, they really have a significant difference. But in GMPN, these two are exactly the same. And now let me end with a conjecture. So this is the extended version of our second theorem, where we remove the requirement of minimum length for the factorization. So this says that for any finite complex reflection group, 2 factorizations of any length, they will be in the same orbit if and only if they generate the same group and they have the same multiset of conjugacy classes. So we know this is true for minimum length, but we believe this is also true for any length. And this is known for the symmetric group. It's an extension of Kluman, Benezek, and Teicher. Also, this has been done for the dihedral group by Sia and Berger. And the exceptional one, so this is called the tetrahedral family of rank 2. This has been done by Joel's undergrad students. So this is not me. And also the case when G is a Coxeter element. In the real case, it's been done by Lewis and Reiner in 2016 recently, and the case when is in GM1N and GMMN, also done by Lewis in 2020. So all of these indicates that this conjecture is probably true. So on that positive note, I will end my talk, and thank you very much for listening and participating.
Thank you very much for the wonderful talk. Please, you can express thanks on the chat on the screen. And are there any questions for Jiayuan?
Has anyone tried to look for a counterexample for the conjecture explicitly? Like, has anybody had net hope and actually?
As far as I know, I don't know, but also I'm seeing Theo shaking his head, so probably no one has found a counterexample.
Not found, but like really tried to find one.
And sometimes you try to prove it for the exceptional groups, so that is, it doesn't answer your question because you don't try to disprove it, you try to prove it, but then when the calculation completes, you have not disproved it. So it's very difficult when you have higher length, it's not computationally feasible for.
Yeah.
So I have a question. So for these formulas to compute even the length, this maximization problem, and then the formula for the number of orbits. Mm-hmm. So are those things like in general hard to compute, even like the maximization, even finding the partition that maximizes?
Yeah. So actually, to find all the cycle partition that will maximum the value, this is really hard, and in fact, I think it's NP hard. Yeah, so it's very difficult computationally speaking.
And I have another question. So you gave some criteria for like some special groups, for the dihedral. Yeah. So like in terms of there's only 2 cycles that their weights are 0. Do you have one for the subgroup G, like yeah, do you have one for like G, M, and N? Is there something like that that's like a general criteria for?
Yeah, so it's not going to be as nice as this one. So in GMMN, the action will be transitive. Really is this criteria. We need a unique cycle partition, and also for every part, we need ROB to be 1. So I can't do any more explicit description other than these two, because the reason we can come with this direct description is because in GM1N, in order to have a maximum value, either 2 cycles are in the same part or every cycle is in their individual part. That's how we get the maximum value. But when in GMMN, we don't have that really nice condition. So that's why it's hard to give a direct classification of what the Hurwitz transitive element look like.
Other questions?
Yes, I wanted to ask something. So, like at some point, you're asking. So when you have a theorem that's explicit for GMPN, and then the version of the theorem for arbitrary groups is that the Hurwitz orbits are determined by the group that's generated and by the multitude of conjugacy classes. So if you try to phrase it, let's say, so like if you try to phrase it and say, for an element in a reflection group, the number of Hurwitz orbits is equal to the number of minimal reflection groups that contain it. Then it would be nice if you can give like another geometric version for the number of multisets of conjugacy classes that can appear. Because then you would have like a whole characterization that's kind of like intrinsic. You would say for every element in every reflection group, the number of Hurwitz orbits is equal to the number of minimal reflection subgroups that contain it, and then something with the multiset of conjugacy classes that can appear like that. Is that something you could do?
Yeah, that sounds really nice.
Could be good idea.
Yeah. That could be done.
So on the positive note, let's thank Jiayuan again for the great talk, and see you all